Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. In this we are looking specifically at transfer of heat and heat capacity calculations. We have a good comprehensive problem over here. We have 10 grams of methane gas which are combusting. The heat of reaction is given here, minus 802 kilojoules. That minus tells you it's an exothermic reaction. Anytime you combust a hydrocarbon, you're generating heat. And then this heat is going to be transferred to this other system which will heat up either gold or water. 100 kilograms of gold, 100 kilograms of water. That heat from that combustion reaction is being transferred to that, and we have to find the final temperature of that gold and the water, which were initially at 0 degrees Celsius. The specific heat capacities for gold and water are provided 0.128 and 4.184. Remember, specific heat capacity, when we're talking about heat capacity, we have this equation mc delta T. These are my C values I've provided here. The C is 0.128 and 4.184. If you're interested in units, just solve for C. You'll have H over MT. The units for H here will be joules. The unit here for mass will be grams, and the temperature degrees Celsius. So that gives you the units of these items, 0.128 and 4.184 joules per gram Celsius. That's how you determine that. Anyhow, let's get back to our question. 10 grams of methane gas being combusted fully. These full 10 grams, we're transferring the heat to either gold and water, and we have to calculate the final temperature of both of those items. Start here with the equation. You don't always have to do it, but it's not a bad idea to do it. Combustion reactions are always exactly as you see. Carbon dioxide and water, the end products. This is a initial reactant. We have 2 hydrogens times 2, 4, and 4 hydrogens, 1 carbon, we're good. We have 4 oxygens, so therefore we put 2 over here and we're good. We have to determine the moles of methane, because that'll come in very handy in terms of that item we have over there. We have 10 grams over here of methane gas divided by, what's the molar weight or the molar mass of it? It's 16 grams. 16 grams per mole of methane, and when you do this, you'll do 10 divided by 16, you get 0.625 moles of methane. But remember, each mole, if you were to combust each mole, the delta H of this specific reaction is minus 802. So each mole gives you minus 802 kilojoules. You just multiply this by minus 802 kilojoules per mole methane. Because we're not doing a full mole, we'll get a fraction of that, but it'll be a good amount. These will cancel out, and you'll have a value over here, 0.625 times 802 minus. You'll have minus 501.25 kilojoules. Now this heat is going to get transferred into this system, which will have gold and water. When you're transferring it in, you're going to change the sign to positive, because then that will become an endothermic reaction, because heat will be absorbed by either gold or by either water to raise their temperatures. Now let's look at gold. The gold calculation, remember, it's always mc delta T is equal to the heat capacity. For the heat capacity calculations, that's the formula. This is what's going to come into your value here for H. But remember, when we're talking about heat capacity, it's always in joules. So you have to convert this into joules. You have to multiply that by 1000. It's going to be 501.250. 501.25 times 1000, because you have to convert kilojoules to joules, because the units of these are in joules, as you know, is equal to your mass. Here we have 100 kilograms, you have to convert that into grams. 100 and 1000 grams, 100,000 times 0.128 times delta T. We'll calculate here for delta T. Remember, they're all here at 0 degrees, so it's easy. As you can see, you'll do 501,250 divided by 100,000. And then you'll divide that by 0.128, and you get here 39.16 degrees Celsius. 39.16. If they're initially at 0 degrees, then the final temperature here, TF for gold, will be 39.16 degrees Celsius, and that's done. We can save that value here, 39.16 for gold. Now let's do the exact same calculation, but for water. Looking here specifically at water, water has a higher heat capacity by many times. Therefore, it takes more energy to heat the same amount of water as it would the same amount of a metal, which is why metals are good conductors and water is a poor conductor. Here we'll have 4.184. Now we'll send this to the calculation and calculate for delta T. We'll do 501,250 divided by that 100,000, which translates to 100 kilograms. We'll divide this by 4.184, and we get here 1.19, which I'll round to 1.2 degrees Celsius, and that's my value here for water. The same amount of heat transferred into both gold and water generates a considerable increase in the temperature of gold, but not so much for water, because gold has a very low specific heat capacity. It can absorb heat very easily and it can change its temperature. Water has a very high heat capacity, especially in large volumes. Therefore, the temperature rise is very minuscule, 1.2 degrees Celsius for water versus 39.16 degrees Celsius for gold. And that right there brings us to the end of this calculation. You can see how we did the transfer of heat from an exothermic into an endothermic reaction. The sign changed for the heat. Everything here is in proper units in terms of joules for your heat capacity calculations. Exothermic, endothermic reactions are here in terms of kilojoules, but you convert them. The kilograms are in terms of grams, and everything else follows as you see. And that brings us right here to the end of this video. Thank you for watching. Have a good day.